Hello again everyone, and welcome to another video. This time we're going to be starting on compiler design. Our first lesson is going to concern the definition of a compiler and the phases of a compiler. Now, a compiler is a program that translates a piece of code from one language to another. And I'll be taking notes as I talk, just to make your life easier if you want to take notes as well. So, a compiler can also be defined as a program that translates high-level code to machine code. But we're going to define it as a program that translates code from one language to another, but in general, translates high-level code to machine code. Okay, now as well as a compiler, we have interpreters. So an interpreter directly executes code rather than translating it into machine code and then executing it. So what it does is it passes the code statement by statement and executes it statement by statement. So no translation. Now for a compiler, of course, the machine code is executable, whereas the interpreter, it doesn't produce anything directly executable. It has to pass the entire code, the entire piece of code, statement by statement, and then execute it as such. So this is quicker, whereas this results in better error diagnostics. Because since every piece of code is executed statement by statement, you know what's happened and where it's happened when an error occurs. So now let's take a look at the phases of a compiler. The first phase is the Lexing phase. Now, in this phase, the compiler scans an input of a sequence of characters, basically, that are then placed into tokens. So the code is scanned as a sequence of characters, and the every group of characters that is meaningful is assigned a token. So to visualize that, we can have a piece of code such as this: number is equal to 50. Now, this as token form, this is going to be represented as such. So the number is a variable, isn't it? So the lexeme, or the symbol used to represent this number, is going to be var, for instance, for variable. Now this can be something else based on what sort of compiler you've got, but let's just call it var, and then it's going to have 1 here, and the 1 is pointing to a particular row in the symbol table, which we're going to get onto in a moment, and this is going to store the value of it, basically the value of the token. So we're going to have var1, and let's just this way, and we're going to have equal sign. The equal sign is not going to have an entry in the symbol table because it doesn't have a particular value that needs to be associated with it. It's just an equal sign. And then we have num. So the type of this 50 basically is a number, and it's going to be pointing to row 2 in the symbol table. And then finally we have EOF, which stands for end of file, because the semicolon there stands for the very end of this particular piece of code, effectively. Now, what the pointing to the symbol table means is, for instance, the symbol table for this particular piece of code is going to be 1 to represent row 1, and then number, and then dash to represent an empty column. So the first column is the number that is associated with this particular token. This is the name of the variable. So in this case, it's number. And then this is going to be the value associated with this particular token, but in this case we're not storing a value, we're just storing the name of the variable, so we store it as such. And then the second row is going to be num, again, because it's just a number. So we're not actually storing a variable name, it's already we've already named it number effectively. And then 50, because we're storing a value of 50 associated with this number token. Now we're going to go into more detail later, so don't worry too much. And let's just get on to the next phase of compiling. So we have syntax analysis next. Syntax analysis involves identifying the structure of the program. This is done with a grammar, and we're going to learn about grammars soon, maybe even in the next video, so don't worry about this too much, but this effectively runs through the code and it identifies the structure based on what it sees. So it breaks everything down and it associates, variables with operators that leads to another variable, and so on and so forth. But don't worry too much about this. And next, and just one more thing about syntax analysis, it produces a parse or syntax tree. And this is where the structural information of the program is stored. Next is semantic analysis. Semantic analysis is going to be about the actual semantics of the piece of the program. So it verifies if the program is meaningful, basically. So has meaning. Now, a large part of this is going to be type checking, and let me show you this as an example so you understand what semantic analysis is. If we were to have, say in Java, 5 plus hello, this is wrong, isn't it? Like this, you can't add an integer and a string. If this were to be two strings, then you could concatenate them. If they were two integers, then you could add them together. But in this case, there's nothing we can do. So this would have to output an error. Now, the Lexing stage and the syntax analysis stage can't do anything about this. This is what the semantic analysis stage is for. So we're going to go into more detail again later, so don't worry too much about it. And the next stage is intermediate code generation. What happens here is the high-level code is translated into something in between high-level and machine code. Now, this is done to smooth the transition. In fact, you can think of it that way for now, to smooth the transition between high-level and machine code. And there is more detail here to go into, but again, it deserves a video of its own. We can't go over everything in this one video. So let's just move on to the next stage, and that is code optimization. Now, this can happen anywhere, in any of the phases, pretty much, but in general, it's done to the intermediate code and to the machine code. So it'll also often be done once as machine-independent code optimization, and once as machine-dependent code optimization. So the machine-independent code optimization is done on intermediate code. Machine-dependent optimization is done on machine code. Now, effectively, this is done to produce more efficient, faster, or shorter code, or all of these. It's aiming for any of these, basically. And for obvious reasons, this is advantageous. You know, you can make your code take up less space, you can make it faster, and so on and so forth. There might be things that you've missed, or there's things that can be cut out, basically, and there's things that can be made faster in machine code. So the next step is target code generation. And this can also be called machine code generation. This takes the intermediate code and it translates the intermediate code into machine code. And that's effectively all that is. So for now, we've looked over what a compiler is, very roughly, and we've gone over the phases of a compiler. We've taken a bird's eye look at the phases of a compiler. In our later videos, we're going to go into much more detail on each phase, and we're also going to learn about grammars and finite automata. So stay tuned in if you'd like to find out more. I hope you enjoyed this video, and I'd like to see you again next time. Thank you for watching.